please take it over, Dustin.
Okay, thanks, Jeremy. Nice to see everyone back again. So I'm going to be starting to talk about solid abelian groups, which are a certain full subcategory of condensed abelian groups. And let me start by explaining the idea. Well, we want some kind of completeness condition. To put on a condensed abelian groups, to put on condensed abelian groups. Why? Why do we want that? Well, Peter explained basically that basically Homs and even R-Homs, well, and even internal R-Homs, I guess, in condensed abelian groups are good in the sense that you get reasonable answers when you plug in familiar examples of condensed abelian groups. Well, we saw locally compact abelian groups and we saw infinite products of copies of Z. And actually you can build a lot of things just from those. And it implies that all these calculations are going to work out well in condensed abelian groups. However, there's another algebraic operation we like to perform called the tensor product. And there is a tensor product. On condensed abelian groups. It's determined by that if you take a Z bracket S tensor Z bracket T, you get Z bracket S times T. And it has a derived functor, which is, characterized by this only for compact projectives, and in general is given by resolving both variables in terms of compact projectives, and then taking the total complex. If you take familiar things like ZP tensor ZP or ZP tensor ZL or things like this, if you try to calculate certain tensor products, these are big and wild. Condensed abelian groups. Why? In fact, ZP tensor ZP, if you evaluate it on a point, or more generally, well, then you just get a ZP tensor, the algebraic tensor product. So you take the discrete group ZP and tensor it over Z with the discrete group ZP, and this is some huge thing because what is ZP as a Z module? It's just some huge, uncountably dimensional, so to speak, flat Z module. So if you were even to tensor with Q, you'd get some uncountable Q vector space. It's just some crazy thing. And so what we've produced is some condensed structure on this algebraic tensor product. And that's not a very reasonable thing to work with. You don't want to spend your time contemplating this object. So we'd rather have a completed tensor product. Some ZP tensor completed ZP, which should, in theory, commute with the inverse limit defining ZP, which would give this idempotency result for ZP. And for similar reasons, you would expect ZP and ZL not to interact with each other under a completed tensor product. And the way we'll get this is by positing, well, we'll produce this full subcategory solid Z modules in condensed abelian groups. And it will be it'll be a full subcategory, in fact, closed under all colimits and limits. And there will exist a left adjoint. So M goes to, we'll write with a solid in the corner here, solid in the upper corner. A left adjoint to the inclusion, so that's a functor going backwards, and then the completed tensor product will be the solid tensor product. So M tensor N solid defined to be equal to the solidification of the usual of the condensed tensor product.
We're assuming M and N are both condensed.
Yeah, so N and M are both, you could take M and M to be condensed, but the result of this will only depend on their solidifications. So you might as well just take M and N to be solid to begin with. Okay. So that's what we want. And this is really, I think, the true test of the setup that we've been explaining to you guys here. I mean, it's not too difficult to produce frameworks where you have good calculations of X and arhms and so on, but to be able to express something like a notion of completeness in a satisfactory way is very difficult. So this is the thing that would, yeah. Once this was in place, it was clear that we had a good theory. And actually, I want to explain that we actually get very strong properties for solid abelian groups. We get greedy. In fact, solid Z will itself be, I already said it's a full subcategory closed under limits and colimits, so it's an abelian category. But it'll also be an abelian category generated by compact projectives. So it fits into this framework of extremely nice abelian categories that we've been emphasizing from the start. And the compact projective generators you can take to be well, the solidifications of the beta S's, I guess. But it will turn out that this will be abstractly isomorphic to some infinite product of copies of Z. So the very thing that Peter described at the end of his last lectures. And then in particular, this being generated by compact projectives means that you have it's very easy to understand, well, to do homological algebra purely within the solid context as well. And these functors relating condensed abelian groups and solid abelian groups have good derived functors that have analogous properties. So the derived functor of the solidification will also be a left adjoint in the derived world. So how are we going to produce this framework or this full subcategory of solid Z modules? So there's two parts to it. One is I'm gonna explain some abstract framework where if you have an abelian category generated by compact projectives, how do you produce good localizations of it? So good full subcategories with a left adjoint, which also will then such that they will also be generated by compact projectives. And the second part is verifying this, carrying out this abstract framework in the context of condensed abelian groups here. So I'll start with the abstract framework. So let A be an abelian category generated by compact projectives. And suppose given a functor, so I'll write ACP for the full subcategory of A consisting of the compact projectives. So I'll call it L, this functor L from CP to A with a natural transformation from the identity functor, by which I mean, I guess, the inclusion, more honestly, such that, and here I'll write the key condition. So if M in A is a co-kernel of a map from some direct sum of copies of some direct sum of copies of something in the essential image of L to something else, to another direct sum of copies of something in the essential image of L, then when you take the arhom from C to M, that's the same thing as the arhom from L of C to M via this the map going the other way, induced by the natural transformation. Okay.
Compact projective.
Did I forget to say projective?
C should be compact projective.
Thank you. Yes. Yeah. For all compact projective C. Okay. So this is going to be the key condition, and if this condition is satisfied, you get a whole host of conclusions. Then, well, first of all, the following two full subcategories of A agree. So the full subcategory of those M and A as above, a co-kernel as above. Or in other words, just anything kind of generated by the essential image of L, you could say, under colimits. Or generated in one step, I suppose, a priori. And the set of a collection of all M and A such that given every map from C to M, there exists a unique extension to a map from L of C. So those following two full subcategories agree and form an abelian category, form abelian subcategories. Closed under all limits and colimits and extensions.
With this question?
Yes.
Would this correspond in classical algebraic language to something called cotorsion theory?
I don't know. I can tell you exactly what if you take A to be a category of modules over a ring, I believe the only localizations you get this way are sort of the usual algebraic localizations given by inverting some element. I think that's an exact characterization of the things that arise this way. So it's quite, I find this quite interesting that in our context, it's very similar to modules over a ring, except you have many generators instead of just one. But now you have localizations like this, which should be like inverting an element, but actually function as completion in practice. So it's quite...
The situation looks like modules over a Noetherian ring, infinitely generated modules over a Noetherian ring, perhaps, analogous.
Yeah, I'm afraid I don't know enough about that setting to be able to comment on that. Yeah, right. So second, the colimit, so L extends uniquely to a colimit preserving functor from A to A. It's sorry for not. I mean, I won't bother giving it new notation. Yeah, it's the colimit preserving extension of L, and the essential image of L equals the full subcategory of 2. Of 1, and L is the left adjoint to the inclusion of this full subcategory. Okay, so we have the situation of a localization functor onto a category which is closed under colimits, and that means that also that the localization functor considered as an endofunctor is closed under all colimits. right? And then there's interaction with the derived context. So, what's the best way to say this? Right, so the similar, it's the colimit preserving, well, we can extend even further L to derived category of A, the colimit preserving extension, which I guess is the derived functor, in other words. Also commutes with colimits, sorry, has essential image, the full subcategory of dA characterized by either I'll just say the derived analogs of 1, by which I mean, so here, in the first description in 1, I say M is generated by co-kernels of direct sums of copies of things. Now I should say that M is represented by a chain complex consisting of direct sums of copies of these things, or that M is some colimit of things in the essential image. So yeah, just basically generated under colimits by the essential image of the L on the compact projectives. And by the derived analog of the second condition here, I mean, you can express this as saying that HOM from C to M is the same as HOM from LCM. And for the derived analog, I would say instead that RHOM from C to M is the same as RHOM from LC to M. Right? Or that all its cohomology objects, homotopy objects, lie in the full subcategory of 1. So you can either characterize it by the derived analog of the condition in 1, or you can actually check it on homotopy groups. I mean, on homology groups, or whatever you like to call the kernel mod image in a chain complex. So in particular, going back here, if you consider M here as sitting some ordinary object in your abelian category, but you can also consider it as a chain complex sitting in degree 0. And so the RHOM condition will also automatically hold here if just the HOM condition holds. Right. And there was, I think, one more thing I wanted to say. Oh yeah, and then this guy is abstractly equal to the derived category of the abelian category in 1. And yeah, this abelian category in 1, maybe I didn't say this yet. Yeah, and then maybe I should have put this at the beginning in 1. Yeah, and with generated by compact projectives. Namely the L of M's for M in a compact projective. So I'm not saying those are all the compact projectives. I'm saying they generate and they are compact projectives. It follows that all the compact projectives are retracts of them. So there's not that big of a difference anyway. Okay, so this is a huge mouthful. It's probably better to give the inclusion functor a name. Yeah. So the point is there's just a condition you need to check. You need to be able to calculate some RHOMs, and then you automatically get, you get this, you get this full subcategory, which is either generated by the images of the things you described or by this mapping condition. And it automatically is a beautiful abelian category, and the inclusion functor has a left adjoint, which does good things for you and satisfies all sorts of good categorical properties, and everything is very nice. So of course there's a lot of, this is one of these kinds of statements in mathematics that takes longer to state than to prove in some sense. For the proof, you basically follow your nose. So let me try to give the idea. Well, so first of all, we need to show that these two full subcategories agree here, this one and this one. But actually that this condition implies this condition is a special case of what we desired. It's just if you replace RHOM by HOM, then you're exactly stating the condition that this one implies this one. Okay, so the only thing you need to see is the reverse. So if you just know this mapping property, how do you know that your M is going to be a co-kernel? So let's take our M. Now we know that we live in A, therefore it can be, so, well, yeah, did I give names to these two conditions here? Let me say condition, I shouldn't use A. Okay, condition C. Oh, I don't know, C is bad too. Condition X, no. Okay, condition X and condition Y. It's just temporary anyway. Right. Suppose condition Y need X. So we take a direct sum of compact projective CI mapping onto M. And then by condition Y, each of these maps from CI into M extends uniquely to L of CI, and then we can collect them together under the direct sum as well. Sorry. So we can extend it like this. And this map was, we choose this surjective, therefore this is also surjective. Right, and then, M satisfies Y, which means it has this mapping property as we desired. Now this also satisfies Y. Because again, as a special case of the condition we are talking about, a particular case of a co-kernel of a map between direct sums is just a direct sum. So that thing certainly satisfies all of these, satisfies this condition, and therefore, yeah, it satisfies Y. But the collection of objects satisfying Y is closed under limits, in particular kernels. So the kernel, which if we call this the kernel M prime, then this also satisfies Y. And then by the same argument, we can surject onto this from a direct sum of copies of L of DI, yeah? And then in total, we've written M as a co-kernel of a direct sum of copies of L of CI. Okay? So that shows that these two conditions are equivalent. Why are they abelian subcategories, or why are they closed under, well, why are they closed under all colimits, for example? It's not quite obvious from this description. I mean, it looks like this description is closed up under all colimits, but you really do need to check that if you make a map between two such things, that you can lift it to the terms defining the co-kernel and then take the co-kernel there. But you can do that essentially by the mapping property you have on the level of compact projectors. You can always make enough lifts to argue that a co-kernel of things of this form is also of this form. So that is the essence of this here. And that these are compact projective generators. Well, they're generators by construction, and then they're compact projectives, again, by this mapping property coming from condition Y. And then again, for the same mapping property reason, it's not too difficult to see that this colimit preserving functor gives the left adjoint, and well, all this derived category stuff, you kind of just have to look and see. It was a little bit surprising, I think, to us that that you can check the condition on homotopy groups, but it's also just it's a quite simple argument. You just keep doing, this is the only trick you have, and you just keep using it over and over again, of writing your object as building a presentation of your object in the A world, and then applying L to move it into the L of A world. Okay, are there any questions about that bit of abstraction there? Okay, well, I do want to make one what's it called, refinement, or refinement. If A has a tensor structure, commuting with colimits in each variable, and if we have the condition, the main condition star, not just for Arham, but also for underline RHOM, so internal RHOM, then we get more, a unique tensor product on the essential image of A, making A goes to making this L functor, this left adjoint symmetric monoidal. Namely, you take the tensor product in A and then you apply L to it.
Did you make an extra assumption just now?
Yeah, I assume
sorry,
the condition holds for RHOM underline instead of just RHOM.
Right.
Yeah. So then you get a nice tensor product in play too, as well, is what I'm trying to say.
Again, you must perhaps the original tensor product is symmetric on the original.
Yeah, I meant a symmetric monoidal structure here. Yeah, but I'll make a remark that, yeah, so, well, we don't require that the compact projectives be closed under the tensor product. And in fact, in condensed abelian groups, it's not. So you can just keep that remark in your head for a second. I want to make another remark, which is that there's some freedom in how we phrase this condition star. So star, this main condition that you need to check. Star is also equivalent to a somewhat, this sort of same statement, but with kernel instead of co-kernel. So this is actually a useful remark, maybe not for the solid case, but at least in the liquid case, I think this is a useful remark. So let me go back to the condition star so we can look at it. Right, so here I said M is a co-kernel of maps between direct sums, but you can equally well say kernel. Why? Well, you have a exact complex with 4 terms. 0 goes to kernel, goes to direct sum, goes to direct sum, goes to co-kernel. And since we're controlling the RHOMs in every case, if you know the statement for 3 out of 4 of them, then you know it for the 4th. But we know it, but the case of a direct sum of copies of L of MIs is both a special case of the kernel statement and of the co-kernel statement, right? Because you either take the 0 map. So yeah, so you could switch from co-kernel to co-kernel as desired. It's also equivalent to same statement, but with a complex in homological non-negative degrees with terms, direct sum L of MI. So for actually, it's enough to require the statement for a whole, complex. And so then RHOM in the sense of, maps in the derived category, basically, from your thing sitting in degree 0 to this whole complex. Okay. All right. So now I want to explain how exactly we're going to apply this this statement for solid abelian groups. So we need a functor from compact projective condensed abelian groups to condensed abelian groups, which is going to be specifying in the sense sort of the completion of the free thing z z bracket s, or s extremely disconnected. So what do we do? So, well, what we're going to do is this. So if S is extremely disconnected profinite set, Z bracket S solid to be the inverse limit over, well, SI of Z bracket SI or S. Yeah. So you write S as an inverse limit of finite sets. And then instead of taking Z of the inverse limit of the SI, you take the inverse limit of the Z of the SI. Okay. So actually, another small remark is we don't actually need to produce the, well, okay. Note there is a map. There is a map from Z bracket S to Z bracket S solid, punctorial in S, just because of the description, basically. And we don't actually need to prove that Z bracket S solid is punctorial in the condensed abelian group Z bracket S, because if we do prove this universal property, this condition star, then the functoriality will be unique and automatic anyway. So I won't bother addressing that. All we need, we don't really need a natural transformation is what I'm trying to say. We just need a map, and then we're checking some universal property anyway. So it'll have to be uniquely a natural transformation. Okay, so what we need is to verify star. So in other words, we need to be able to control R-harms. We need to understand the difference between R-harms out of Z bracket S and R-harms out of Z bracket S solid. Now we understand R-harms out of Z bracket S. By definition, those are just the S-valued points of whatever you're mapping into. So the key thing is that we need to be able to control R-harms, or in fact, indeed internal R-harms out of Z bracket S star. And the first remark is the following. Well, yeah. Well, sorry, let me make the remark and then I'll state the theorem. So note, well, this is kind of dual to so if we can look at continuous functions from S to Z and then take the Z linear dual of that, or maybe I should probably be working in condensed abelian groups here. So I want a condensed abelian group, so I should take the internal Hom in condensed abelian groups. And in fact, it's also the internal R-Hom. So why is that? Well, this continuous functions from S to Z, this is just the filtered colimit over, do I want it? No, maybe I have to wait to justify this, the internal R-Hom. Yeah, continuous functions from Si to Z.
Pardon, your Homs and R-Homs are within the ambient category of indensed or derived category of condensed abelian groups?
That's correct. Yes, that's correct. Yeah. Right, because the locally constant function from S to discrete space always factors through a finite quotient. So this is the filtered colimit of all these things. And then when we take R-Hom, we'll get a filtered inverse limit of, well, we'll get exactly this filtered inverse limit of product of copies here. Right. So that's at least we know that with the Hom, not necessarily the R-Hom. But then the structure of this thing is severely simplified due to the following theorem of was it Specker?
Yes,
What was the name? Yeah. Sorry, I should have looked it up. So this is we could have defined this as the internal Hom in
Specker.
Specker. Okay, thank you. In condensed sets, but it is discrete. The same argument works. I mean, this argument shows that this isn't filtered colimit in condensed sets, a discrete thing. So this is a discrete abelian group, and Specker theorem tells you that it's a free abelian group. A free abelian group. And this is true for any profinite set. Well, for any compact Hausdorff, doesn't matter. Profinite set S. The statements for compact Hausdorff spaces and profinite sets are actually equivalent, so it doesn't. Yes, this is a non-obvious theorem, which I won't get into the proof. You can find an exposition of it in Peter's lecture notes, condensed.pdf. But Well, one thing you learn from this is that the HOM is the same as the R HOM, because this is a direct sum of copies of Z, so it's going to be projective in condensed abelian groups. Z is a projective object, so it's a direct sum of copies of Z. So I could stick the R HOM in there if I wanted. But you also learn exactly what this is. This ZS solid for any S is for some set I, which we won't specify. Although of course the cardinality is bounded in terms of S, infinite product of copies of Z. So this is the kind of thing that Peter calculated some instances of in the previous lecture. So the most basic case of what we need is the following. Would be that if you take R HOM to some direct sum of, so now we are supposed to take something in the essential image of L, but we just said that everything like that is of this form infinite product. So we have to take a direct sum over some J of some infinite product of copies of Z. In theory, it should be, the index set I here should be allowed to vary, but it doesn't actually matter because you can increase it and it'll be a retract. But let me just say, for simplicity of notation, I'll take the index set I to be the same. We need this to be the same thing as the R HOMs from Z bracket S, which is the same thing as a direct sum of copies of J, product of copies of I, Z, evaluated on S. And you can commute both these operations past the S if you like. So this is because S is extremely disconnected. Right. But the point is really we need to be able to control this guy over here. And we just saw this is going to be for some set I. Now I should be careful. Maybe a different I. Not that it matters. Let me just keep the same I. I mean, obviously all these sets I should be allowed to be different, but for simplicity of notation, let me just take the same I. Now, of course, so what I'll explain is how to calculate this, okay? And of course, you have, and we'll see that it lives in degree 0 and it looks like this. Now, of course, to make an honest argument, you have to make sure that the identification is the same as the map I already wrote down. But I mean, hopefully you'll believe me that that's not the meat of it. So, so how do we control this? Well, we already saw in Peter's lecture that if you take R HOM from product of copies of Z to Z, this is direct sum of copies of Z. This implies that if you take R HOM from product of copies of Z to product of copies of Z, you get product of copies of direct sum of copies of Z because of infinite products is exact. Which means you can pull the infinite product out of an R HOM in the second variable. And that again relies on these compact projective generators. But now we seem to be a little bit stuck when it comes to pulling out the direct sum, because for that we'd have to have this be, in theory, we'd need this to be a compact object if we wanted to pull out a direct sum there, but it's actually not. So the things that are close to being compact objects are like the compact the compact topological groups, for example, compact abelian groups, but this is very much not a compact abelian group. So we have to use the same trick that came up in Peter's lecture of relating this. So to go further, we have to use the same basic trick. Right. So we use this resolution here. And now recall, recall that from the Breen-Deligne resolution, implies that any compact abelian group is resolved by compact abelian group A is resolved by copies of Z bracket A, and then these can be Z bracket A's, well, or products of copies of A, but that's also a compact abelian group, can be resolved by Z bracket S for S extremely disconnected by choosing a hypercover of the, by choosing hypercover. Since A is a compact Hausdorff space, we can make a hypercover by extremely disconnected. So we can resolve A by these ZAs, or things similar, yeah, products of copies of Z of products of copies of A, and then we can resolve each of those by extremely disconnected. And in total, taking a double complex or whatever, we find that A is resolved by compact projectives. So A admits a resolution where each term is a compact projective object in the category. And so that is what that's what's known as pseudo-coherent, or in the language of SGA, or almost perfect. Well, I shouldn't use perfect. No, almost compact, I guess. Never mind that. Pseudo-coherent is the usual terminology for something like this. And this implies, in fact, it is equivalent to, yeah, I think it's equivalent, that for that any x'd I from A, that all these x'd I's commute with filtered colimits. Or infinite direct sums, if you like. Since we already know it commutes with finite direct sums being an exact functor. Okay. So then we can go back here. Right. So now that I just explained that for this term, we have no problem commuting the direct sum out of, for the Arham mapping out of there. So now we only have to worry about this term here. But there we're going to use the same trick. So so only need to control product of copies of R to a direct sum of product of copies of Z. But again, we have Arham R direct sum product of Z equals 0. And even internal Arham. Why? Well, we use the same short exact sequence again. Again, we can control this guy. Now it's just one copy of R mod Z, but we can still pull out the direct sum there. And we can control this guy. Z is also a compact projective, so we can pull out the direct sum. So it follows, oh wait, sorry. Maybe I should just make the remark. Sorry, I'll just make this remark once and for all. We have this short exact sequence, which then implies that R is also pseudo-coherent. So these pseudo-coherent modules have a 2 out of 3 property in short exact sequences. You can just splice resolutions together. Right, so we can pull the Arham out of the direct sum, and then we're reduced to Arham from R to product of copies of Z, or again to Arham from R to Z, which is exactly what Peter handled in the previous lecture. I should also say, yeah, pseudo-coherent things is not just X's that commute with X out that commute with filtered columns, but also internal X out will commute with filtered colimits. So even though the product of tensor product of 2 compact projectives is not compact projective, it will still have a resolution by compact projectives because it corresponds to the product of the extremely disconnected spaces, which though not extremely disconnected are still compact and can still be resolved. Okay. Right. So where am I? So in conclusion, I think what I've explained is that one can in principle calculate what this Arham is here. And when you actually put it together, what do you find? Well, so you can switch it over to R mod Z's, because this one vanishes. Then that one you can pull out the direct sum, and it follows that you can pull out the direct sum in general. And then you get and you can even control the internal Arham if you want. So this is going to be direct sum of Arham product of copies of Z to product of copies of Z, which is direct sum product direct sum Arham ZZ, which is Z. Okay, and then you can look over to the other side of the equation and see if it doesn't look similar. Right, so it's a direct sum of a product of, but continuous functions on S with values in Z was by Specker's theorem also a direct sum of copies of Z. So they look the same, and when you're a little more careful, you see that the identification is actually identifying them. And that's how you do the most basic case of what you need to prove. So the case of just mapping to a direct sum of copies of things and not mapping to a co-kernel of a direct sum of products of copies of things. Okay, so now I'm debating with myself how much of the rest of the argument I actually want to go into. I'll tell you what, let's table the rest. Well, if we have time at the end of next lecture, say, then I can fill it with this. So to do the general case is more complicated. I mean, but in the end, you always use these similar tricks, yeah? You replace some products of z's with products of R mod z's, which you can control because it's a compact abelian group. But the way in which you leverage this trick becomes slightly more complicated and technical to handle the general case of a co-kernel of a direct sum of copies. But so I'll get back to it if I have time at the end. But maybe I've done enough of the technical stuff for now, and I want to make some more general comments. Okay, so let's step back and let me make some remarks. All right, actually, are there any questions? No, okay. Well, first of all, let's see that it does what we want it to do. How to calculate with this? How to calculate solid tensor products? I mean, the first thing you need to know is how do you tensor product? Well, the solid tensor product is going to commute with both colimits and both variables just for formal reasons. And so what you do is you resolve by these and then use the following fact. If you take product Z solid tensor product, or even derived solid tensor product, product JZ, this is the same thing as product I cross J Z. So this kind of infinite distributivity, which is, you could think of as being kind of characteristic of a completed tensor product. You can commute your tensor product with certain limits, yeah? And this follows, by the way, by if you write this as continuous functions on the solidification of continuous functions on something, then and do the same thing here, then calculate on the level of, yeah. Sorry, solidification of not continuous functions, but the free condensed abelian group on some profinite set, and then compare. So in general, this is how you calculate. You know in principle that any solid thing can be expressed in terms of products of copies of Z. It's generated on equivalence by there. And then you use this basic fact there, and then you build it up under colimits. So let's do some examples. So yeah, ZP, tensor ZP. So how can we write ZP in terms of these compact projectives? In fact, it emits a very short resolution. So you can write this. You can take the power series ring in one variable over Z, which is just as an abelian group, an infinite product with copies of Z, countable. And then you can mod that out by T minus P. So this is a nice way of thinking about the p-adic integers. It's like power series in Z, but where the variable is set to P, right? That's kind of, so in fact, you can see that this is a short exact sequence in condensed abelian groups. So it's a length 2 resolution of the thing you're trying to calculate. And then you can just work it out, yeah? So you do this and this, and you get it, you work it out and you get ZP. So yeah, just have to, yeah. You kind of have to do the calculation, but actually more generally, if A and B are profinite abelian groups, then the solid tensor product commutes with filtered inverse limits. So it is kind of the completed tensor product you'd expect for profinite abelian groups. Lars, yes, this one here is also the derived solid tensor product. Yeah, this one isn't because it is if you say derived. Wait, no, hold on a second. Yeah, I mean, yeah, FP tensor FP is going to have something in degree 1, just like usual. Yeah. But yeah, in general, it's also usually a good idea to do the calculations in the derived way, and then just look in the end whether it's concentrated in degree 0 or not. Yeah, and then you can also calculate the ZP tensor solid ZL for L different from P is 0. I guess it's also a special case of what I just said. What are some other calculations? So these are calculations of things which are actually sort of which have, well, we haven't done any infinite direct sums yet. This is all compact things. But you can do some things with infinite direct sums as well. So for example, yeah, well, if you take product of copies of Z, you could tensor it with ZP. And then here, since this is resolved by 2 copies of products of copies of Z, you'll see that this will commute with the infinite product, and you'll get product of copies of ZP. But if you take tensor it with QP, then since the tensor product commutes with colimits, then you can write QP as ZP with P inverted, and that'll pass through the infinite product. So you get this here. So you get it's the subset of the infinite product of QP, consisting of ones with a bounded p-adic valuation. So that's kind of how things work. Let me mention something that I'll talk about later. So so in principle, you can always calculate everything because you can build your thing in terms of these compact projectives and just do what you need to do. But actually, sometimes it's quite intricate. So let me give you a statement an advertisement for the p-adic functional analysis that we're going to do a little later, which is that if V and W are Frechet spaces over QP, and then you view them as solid abelian groups. So a Frechet space is a certain kind of metrizable space, right? So you can put this, it's compactly generated, you can put it inside condensed abelian groups, and it will be solid because it's an inverse limit of Banach spaces, and solid abelian groups are closed under limits, so it suffices to see that a Banach space is solid. But a Banach space is of the form, you take the unit ball and then invert P, so that's a colimit, and solid abelian groups are closed under colimits, so it suffices to see that the Banach ball is solid, but the Banach ball is the inverse limit of its reductions mod P to the n, and each of those are discrete. So everything discrete is, everything discrete is solid because Z is, and then you're closed under colimits. So then you take discrete things, take inverse limits of them, and then take colimits of that, and then take inverse limits again, and you get a Frechet space. And that proves that Frechet spaces are solid, because solid is closed under everything, limits and colimits. Right, then the solid tensor product is the same thing as the projective tensor product. I don't know why I switched B and W there, but it's symmetric monoidal, so thankfully I don't have to erase it. It's a true statement. So this is actually quite subtle because the solid tensor product is built from colimits by compact things, whereas by definition, this completed tensor product is the inverse limits on the level of Banach spaces. So this is a little bit subtle to prove, but anyway, the point of giving all these examples is that in practice, this solid tensor product does work like a completed tensor product. Right, so that's good. So it does what we wanted it to. And let me I have many remarks to make about this solid situation. One thing which actually came out of the proof, which is part of the proof, is that the solidification of the real numbers is 0. So actually in the course of the proof, we had to show that there are no R-hums from R to any of these things that we're talking about. So what this means is that, so if solidification is a, yeah, well, the moral of this is that solidification is very much a non-Archimedean kind of completion. Or it behaves like, it's like completion with respect to a linear topology. So a topology, it's more similar to completion with respect to a linear topology, a topology defined by a neighborhood basis consisting of abelian subgroups. Yeah, so whereas R just can't be seen. Okay. But now actually I want to take apart this analogy with completion just a second. I want to discuss the extent to which solidification is like completion and the extent to which it's not like completion, even like completion with respect to a linear topology. So why is solidification, or why is solid like complete? Let me put it that way. Well, we already saw in examples that the solid tensor product behaves like the completed tensor product, but let's just look at the definition, in fact. So in one characterization of when an abelian group is solid, a condensed abelian group is solid, is that if you have a continuous map from S to M, then it should extend uniquely to this Z bracket S solid. Now, I'll also recall for you that this was the dual to the space of continuous functions on S. So you can also think of this as a space of measures on S. And so what this condition is saying is that if you have a map from a priori an extremely disconnected S, I'll explain what this functor does to a general S in just a second. But if you have a map from an extremely disconnected S, it'll also work for profinite. So if you have a map there, a continuous map there, then you can integrate it against any measure. Yeah. So extending to Z bracket S, just a free condensed abelian group, that's automatic. But this kind of closes, this embeds densely in there, and so you're adding a lot of limit points, which actually amounts to certain infinite linear combinations of elements of S, as long as they satisfy some prescription, keeps control of them. And so this is very much like being able to integrate functions, integrate continuous functions, which is the hallmark of, well, one thing you need completeness for, very important application of completeness. But why is it not like completeness? Well, for the first thing, it's only complete on the compacts. So in general, if you have a topological abelian group, the completion is defined in terms of open neighborhoods of the identity, yeah, and so it kind of uses the open subsets in the topology, and it kind of goes all over the place, so to speak. But here, this condition is sort of purely, it's all happening in terms of compact subsets mapping, and as it kind of has to in the condensed framework. That's the only thing we're really allowed to discuss. So it's actually, it's closer to, in terms of functional analysis, it's closer to what's called quasi-completeness, which is kind of a way of expressing what complete only on the, as far as the compacts are concerned. But there's another important difference of this with the notion of completeness, which is that it has nothing to do with Hausdorffness. No connection to Hausdorff. So again, there have to be a bunch of non-Hausdorff examples of solid abelian groups, just because solid abelian groups form an abelian category. So you could take, for example, product of copies of Z, and then do it again with the discrete topology, or I could just take direct sum of copies of Z, nothing, the product of copies of Z. So same index set, say. and then take the quotient. This will be non-Hausdorff, but solid. Or non-separated, non-quasi-separated. But it has to be solid because solid abelian groups form an abelian category. Right, so what's going on? Now, usually you might be used to, okay, then you might think, okay, well, completeness doesn't have to have Hausdorff because completeness is exists a unique, and you could just say exists. That's the classical way of weakening completeness to make it not force Hausdorff, right? Not every Cauchy sequence should have a limit, or should have a unique limit, but it should have a limit, yeah? But this is different because it is an exists unique thing. And yet it still doesn't force you to be Hausdorff. So what's going on is that because again, you're only requiring what's going on for mappings from a compact set, you're already asking for a lot of limit points of your original function. So it's not like a Cauchy sequence and then you need to produce a limit. You're already giving yourself a lot of limit points because you have a compactum. And then you just ask to have more in the presence of this algebraic structure of addition, so that these limit points combine in the unique way on the compactum. Okay, I am out of time for now, so I'll continue making remarks after the break.
Okay, thank you very much, Dustin.